Hello friends, welcome to the tutorial series on network analysis made simple. In this tutorial, we shall discuss on Q factor of a series resonance circuit. Before we start the discussion on Q factor, we shall review briefly about the previous tutorial on series resonance circuit. The first point is at resonance XL is equal to XC. Impedance will be purely resistive and hence Z is equal to R. Current will be in phase with the applied voltage and is maximum at resonance and I naught is equal to V divided by R at resonance. Power factor of a resonant circuit is unity at resonance. At off resonance frequency, when F is greater than F0, the inductive reactance is more dominating than the capacitive reactance and hence the total impedance will be inductive. At off resonance frequencies, when F is less than F0, the capacitive reactance is more dominating than the inductive reactance and hence the total impedance will be capacitive. First, let us know what is a Q factor. It is the sharpness of the frequency response curve. We know that frequency response is the variation of current in the circuit as the frequency of the applied voltage changes. More the sharpness of the curve, larger the Q factor. We shall see more about this in the next discussion. Q factor also is defined as the ratio of voltage across inductance VL to the voltage across the resistance VR of the circuit. Or it also is defined as the ratio of voltage across the capacitance VC to the voltage across the resistance VR. But we know VL is equal to I naught into XL and VC is equal to I naught into XC and VR is equal to I naught into R at resonance. By substituting for VL, VC and VR, we get Q is equal to omega naught L by R or Q also is equal to 1 divided by omega naught CR. Friends, we know that Q is equal to omega naught L divided by R. But omega naught square is equal to 1 divided by LC. So, omega naught is equal to 1 divided by root of L into C. By substituting, we get Q is equal to 1 divided by root of L into C into L divided by R. By solving, we get Q is equal to 1 divided by R into root of L divided by C. Next, we shall discuss about the Q rise of voltage across the resonating elements L and C. Friends, you will be surprised to know about Q rise of voltage across the resonating elements L and C. This I will clear in the next subsequent discussion. Consider a simple RLC series resonance circuit. Let the voltage applied be 10 volts at a resonance frequency of say F0. Let the Q of the circuit be 50. Then at resonance, voltage across L VL will be equal to 500 volts and voltage across C VC also will be equal to 500 volts. Let us see how it happens. We know voltage across L VL is equal to I naught into XL. But at resonance, I naught is equal to V divided by R. So, by substituting for I naught, we get VL is equal to V divided by R into XL. But XL is equal to omega naught L. Hence, VL is equal to V into omega naught L divided by R. But we know Q is equal to omega naught L by R. By substituting for Q, we get VL is equal to V into Q. At resonance, we know XL is equal to XC. So, voltage across C, VC also will be equal to V into Q. And this we call it as V rise of voltage across the resonating elements. Friends, now we shall discuss about the behavior of resonating elements against frequency. We know that below F0, XC is greater than XL, hence current I leads the supply voltage Vs. At F0, Xc is equal to XL, hence current I and the supply voltage Vs are in phase with each other. Above F0, XL is greater than Xc, hence current I will lag behind the supply voltage Vs as shown. Further, the variation of phase angle phi against the frequency is shown in figure. Notice also that the phase angle phi is positive for frequencies above F0 and negative for frequencies below F0. Friends, finally, let us discuss the pattern of variation of reactance of resonating elements L and C against frequency. The graph of inductive reactance against frequency is a straight line linear curve. The inductive reactance value of an inductor increases linearly as the frequency of voltage applied across it increases. Therefore, inductive reactance is a positive and is directly proportional to frequency, that is XL is proportional to F. If either the frequency or the capacitance is increased, the overall capacitive reactance would decrease. As the frequency approaches infinity, the capacitive reactance would reduce to practically zero, causing the circuit element to act like a perfect conductor of 0 ohm. But as the frequency approaches 0 or DC level, the capacitor reactance would rapidly increase up to infinity, causing it to act like a very large resistance, becoming more like an open circuit condition. This means then that the capacitive reactance is inversely proportional to the frequency for any given value of capacitance. Figure shows the variation of both inductive reactance XL and the capacitive reactance XC against frequency. We can see that at resonance, the two reactances cancel each other, thereby making a series LC combination act as a short circuit with only opposition to current flow in a series resonance circuit being the resistance R. In complex form, the resonant frequency is the frequency at which the total impedance of a series RLC circuit becomes purely real. That is, no imaginary impedances exist at resonance. Friends, during this tutorial, the quality factor Q of a series resonance circuit is exhaustively discussed. The definition of Q factor, its different equations, and variation of reactance of resonating elements XL and XC with respect to frequency is discussed in detail. Hope this presentation has ignited some of your thoughts. During the next tutorial, we shall discuss regarding half power frequencies, bandwidth, selectivity of a series resonance circuit and obtain their equations. Thank you for watching this video.